Hello everyone. Thank you for being here. We are Junho and HyunA. Today we are going to talk about Bootkitty multi-OS trust chain compromise from Bootkit to Rootkit. I will start with a short introduction of the speakers and our team. Junho is student at Mokpo National University and he interested in low-level security. HyunA student at Seongshin Women's University and she interested in system security. Our team consists of Jiyoung-kwon, Myung-yeol, and Hyung-kyu-sung, and our advisors are Jin Ho-jung, Young-jin Shim, and Soo-min Hwang. To begin with, we will explore what a bootkit is. A bootkit is type of malware that impacts a system before the operating system starts by hijacking the bootloader or kernel during the boot process. In other words, it is an advanced type of malware that targets the boot process. Unlike a rootkit, which runs at the kernel level, a bootkit runs at an even earlier stage in the firmware or bootloader, allowing them to compromise the system. Therefore, one of its biggest features is that it can control everything after the system boots. Furthermore, in recent years, the bootkit threat has remained persistent, with at least one bootkit analysis report published each year. First, let's explore the core threats. Bootkits are highly stealthy, hiding in the boot process to evade antiviruses and EDRs. They also achieve persistence by implanting themselves into the boot partition or firmware, allowing them to persist every reboot. By gaining control before the kernel rolls, they can hook any code or disable mitigations, which results in persistent compromise. UEFI is a modern firmware interface designed to replace the legacy BIOS. It is responsible for initializing hardware components and launching the operating system during the boot process. Compared to BIOS, UEFI provides a more flexible, modular, and extensible architecture. While BIOS runs in 16-bit real mode and supports only masterable record booting, UEFI runs in 32-bit or 64-bit mode and supports GUID partition table, allowing systems to manage larger storage devices and more partitions. The UEFI boot process proceeds through the following stages: SCC, PI, DXE, BDS, TSL, RT, after the power button is pressed. Among these, the DXE and BDS phases are the most common stages where bootkits are installed or injected. Therefore, let's explore these two pages in more detail. The DXE page is a core stage in the UEFI boot process where most system initialization occurs. During the phase, system management mode drivers and various UEFI drivers, enabling full activation of hardware resources and firmware functionality. Since this phase is executed early in the boot process, a compromise at the DXE stage can corrupt the entire secure boot trust chain, affecting the operating system that follows. For this reason, the DXE page is considered an interesting and valuable attack vector for attackers. The VDS page is executed after the DXE phase and is responsible for identifying bootable devices and selecting and executing the bootloader. During this phase, the UEFI boot manager refers to the boot option list to locate available boot paths such as internal storage, network, or external media. The selected boot device EFI image is then loaded, and control is pressed to the TSL phase, where the bootloader is executed. Since the BDS page represents the final boundary before the operating system takes control. If a malicious EFI image is loaded at this stage, an attacker can hijack the bootloader and gain persistent control before the kernel initialization. Furthermore, the EFI system partition used during the BDS page is accessible from within the operating system, allowing attackers to easily install or replace EFI binaries, making Bootkit installation relatively easy. Because of this, protecting the integrity of the boot process is critical. There are several mitigations to prevent bootkits, and the most important of these is secure boot. Secure boot verifies the signatures of each bootloader and kernel component, blocking the execution of any untrusted code. However, it is not perfect. Various firmware vulnerabilities and configuration mistakes have allowed attackers to bypass secure boot. Once this protection is compromised, a bootkit can freely execute and disable kernel-level mitigations, breaking the entire security chain. Therefore, we developed Bootkitty, a hybrid bootkit rootkit that runs on Windows, Linux, and Android by exploiting these vulnerabilities. It is not simply an implementation of a hybrid bootkit rootkit. It demonstrates that once secure boot is bypassed, any form of bootkit can be installed. Bootkitty hooks the bootloader and kernel to gain control early in the boot process. It's built with environment-specific modules that account for each operating system's architectural differences. On Windows and Linux, attackers modify the bootloader on the boot partition to gain control before the kernel starts. On Android, attackers exploit bootloader vulnerabilities to bypass Android-verified boot and gain control in the early stages of the system. Due to time constraints, this presentation will cover only Bootkitty's Linux and Android. Linux boots in 4 main stages. First, EFI loads the signed shim. Next, shim verifies grub's signature and loads it. Then, grub loads the kernel and the initial RAM disk into memory. Finally, the kernel starts system processes and completes the boot. Then, we will first look at shim. Shim verifies the signature of grub and then loads it. From an attack perspective, there are 2 main points regarding shim. The first is tampering with the shim binary located in the boot partition, and the second is hooking the shim loaded in memory at runtime. Shim simply loads grub and does not participate in kernel loading or system initialization, so it becomes a low-value attack surface. However, if control is gained at the shim stage, the hook can later be extended into the grub stage. In this process, the key part to focus on is the unique authentication mechanisms within shim, the machine owner key system. Machine owner key is an authentication mechanism used in shim. When a user registers their one key in the system, any binary signed with that key is accepted by secure boot as a trusted binary and allowed to execute. However, this structure can be exploited by attackers. If an attacker can register their one machine owner key on the VTM system, binaries signed with that key can easily bypass secure boot and execute malicious code. As a result, shim's machine owner key mechanism serves as a vulnerability point within the secure boot trust chain, allowing an attacker to gain control and extend their attack into the bootloader or kernel stages. Grub is the bootloader. It loads the kernel image into memory and transfers control to it, making it the best point to implement hooks before kernel execution. If an attacker injects code at this stage, they can execute it before the kernel rolls and extend the hook into the kernel, resulting in full system compromise. In the UEFI environment, the start image function must be called to execute an EFI image. Therefore, to obtain information about an arbitrary EFI image or to hooks its execution process, the start image function must be hooked. Therefore, we hooked the start image function at the graph stage to control the kernel loading process. After hooking at the start image point, it becomes possible to hook the compressed kernel space. However, at this stage, the kernel is still in a compressed state, so it is not possible to directly hook all internal kernel functions. Therefore, by additionally hooking the function decompress kernel, which decompresses the kernel, it becomes possible to hook the entire kernel. During the kernel stage, core services such as the init process and security policies are initialized. On Linux, the kernel rolls in two steps. First, the compressed kernel image is loaded into memory at boot. Then the kernel decompresses that image before executing it. These two steps are mapped into different memory regions. Several badging mitigations are applied to protect the kernel. Common examples include AppArmor, SE Linux, and kernel module signing. Among these, kernel module signing serves to verify the signature of kernel modules. Therefore, it is necessary to bypass this verification process in order to load a rootkit. We bypassed the kernel module signing feature to load the rootkit. This bypass is possible because we had already hooked the compressed kernel and gained control over our internal kernel functions. By fetching the beginning of the kernel module signing verification function to return 0, the signature verification always succeeds disabling this mitigation. As a result, the attacker can freely disable any kernel mitigations using this method. There are no longer any mitigations that block our rootkit loading. Therefore, the only remaining task is to load the rootkit into kernel. So how can the rootkit be loaded? Loading the rootkit is simple. Among several methods to load a rootkit from your space, the most simple approach is to use the LD preload technique. The first binary executed right after the kernel boots in the init process. By specifying the LD preload environment variable for the init binary, the shared object is loaded first, and its code is executed. If this shared object is configured to the call of function that loads the kernel module, the rootkit module will be automatically loaded into the kernel. And the original init process will then run normally, allowing the system to boot. Then, how was Bootkitty able to create such a rootkit loading environment from the earliest stage of the boot process? Bootkitty exploits an out-of-bound write vulnerability called logfail, which occurs during the premiere stage, the very first page of the boot process. Through this vulnerability, the attackers can execute arbitrary code, such as registering their one machine owner key in the system, bypassing secure boot. After that, malicious code can be injected throughout the entire boot process. Now, based on this vulnerability, let's explore step by step how Bootkitty gains control over the boot process. We used a USB-based attack scenario. In this scenario, Bootkitty is installed on the system using a bad USB. After installation, The infection automatically proceeds on every reboot, demonstrating how the rootkit is loaded and communicates with a seed server. The attacker executes the bootkitty installer via the USB device. After gaining root privileges, bootkitty is installed into the boot partition. Once the installation is complete, the system is rebooted. And from this point on, the modified boot process begins. First, the attacker hijacks the grub bootloader and injects hooks into the kernel loading process. Next, the decompression function of the compressed kernel space is hooked. Finally, the decompressed kernel is hijacked to disable security mitigations and roast the rootkit. Through this series of steps, the rootkit is loaded into the kernel, and the system becomes fully compromised. In summary, Bootkit completely takes control of the execution flow by sequentially hooking each stage of the Linux boot process, from grub to the compressed and decompressed kernel. Also, this thought demonstrates the attack using a bad US-based installation scenario. Similar infection method can also be implemented through network-based attacks in Linux environments. Now, let's watch the Linux demo. It will focus on Bootkitty's bootkit compromise. Secure boot and lockdown are enabled. The USB is plugged in, and the installation script runs automatically. The script installs the bootkit into the boot partition with root privileges. After the system reboots, the modified boot process executes. The system boots with the bootkit active. As shown in the demo video, the grub and kernel initialization pages are the primary hijack points in Linux.
Next, let's look at the Android boot process. We use the Samsung device for our analysis, and the boot process is divided into several exception levels. First, the code built into the ROM launch at exception level 3 performs the initial boot setup, and then loads the bootloader into memory. Then, the bootloader runs at exception level 1, loads the kernel into memory, and prepares to start the kernel. Finally, the kernel runs at exception level 1, loads the main process, and completes the boot. First is the ROM stage. The ROM runs first when the system boots, and it is responsible for loading the bootloader. The code executes at exception level 3, and it embedded in hardware, so it is hard to reach with software attacks and has few known vulnerabilities. For than this, ROM is a limited attack surface for attackers. However, if an attacker could install a bootkit in the ROM stage, they could archive persistent control reboots and gain high level of stealth that is difficult to detect. Little kernel is the bootloader that serves as the entry point for kernel execution in the Android boot chain. This stage runs at exception level 1, and it is at this point that Android verifies boot checks the integrity of the kernel image. Therefore, it is a security critical stage. If an attacker compromises this bootloader, they gain an opportunity to bypass kernel level mitigations before the kernel boot. In other words, An attacker could gain control before kernel protection are applied, taking over the entire system. Therefore, we exploited Odin authentication bypass vulnerability to install Bootkit and a custom RAM disk and used heap overflow vulnerability to execute arbitrary code. This allowed us to place a hook that intercepts the control flow just before the bootloader hands control to the kernel. In particular, we pass the boot Linux FTT functions, which is called when the bootloader loads the kernel into memory and prepares to start it, so that it jumps to the bootkit start address in memory instead of the normal kernel entry point. As a result, we are able to disable kernel mitigations and load the rootkit before the kernel begins execution. The Android kernel runs at efficiency level 1 and efficiency level 0 and includes multiple mitigations. For example, real-time kernel protection, SC Linux, RO data memory protection, and capsule check protect the kernel. We identified where the protection logic is invoked and hooked or patched the privilege check functions. Specifically, we changed functions like mark RO data RO and security captable so they always return 0. In this context, the protection functions appear to be called, but the actual checks are not performed, so mitigations are disabled when the kernel runs. After that, we invoked the init of the custom RAM disk we had loaded into memory so that our attack payload runs early in the boot process before normal boot continues. At the same time, the drop kernel modules included in that RAM disk is loaded at boot. Connects to attacker's C2 server, downloads the rootkit modules from the C2 operative location, and then installs and archives it. Because mitigations were already disabled, the loaded rootkit and rootkit without limitation. Therefore, user space security solutions have get difficulty detecting or block it. Bootkit installs a Bootkit by exploiting an Odin authentication bypass vulnerability in the bootloader stage, and then executes arbitrary code during the boot process through the heap overflow vulnerability. These vulnerabilities make it possible to run the Bootkit and inject malicious code into the kernel. Based on these exploits, we will now have a detailed scenario of how Bootkit took control over the boot process. First, the attacker connects the device to a PC via a cable. Then, they exploit a vulnerability to the bootloader. If the exploit is success, Bootkit can be installed into the boot partitions. When the system reboots, the modified boot chain starts automatically and a hooking change runs just before the Android kernel entry. The hooking code runs right before the kernel entry and disables mitigations. After that, the rootkit is loaded into memory. Once this step completes, the rootkit is archived and entire system is compromised. In summary, in the Android boot chain, from the bootloader to the kernel, Bootkit used a bootloader vulnerability to secure an initial foothold, then hooks the kernel to gain full control over the system. Now, let's watch the Android demo. It will focus on Bootkit compromise. The device is connected to the computer and enters the mode. The attacker exploits a bootloader vulnerability to install the bootkit on the boot partition. The system reboots and the modified boot process executes. The system boots with the bootkit active. This demonstration shows how control at the bootloader stage enables per-system compromise. In today's presentation, we explore how Bootkit, a hybrid Bootkit rootkit runs on Windows, Linux, and Android. Hooks at each stage of the boot chain and extend into a rootkit. A bootkit runs before the operating system loads archives persistence across reboots, and can control the system before the kernel is loaded, which makes it more dangerous than a normal rootkit. Therefore, improving boot process hardening and researching boot chain integrity verification will remain important. In today's talk, we couldn't go over BOOTKITTY on Windows and Rootkit deployment and persistence mechanism in each operating system. Also, although we want to explain more, time constraints prevent us from going into detail. Therefore, if you want a deeper understanding of Bootkit and deep insight into Bootkit, please refer to the published paper. We published our Bootkit test machines on Zenodo. The test machine contains only the Windows and Linux Bootkit binaries. You can download and run it to reproduce our results. The Android version could not be made into a virtual machine because it only runs on specific hardware. That concludes the presentation. Thank you for your attention.
When you're hooking the checks, like for you kind of knock out the checks to return 0 for many of the systems. How do you do how do you find them? Is it signature based on like the assembly bytes? Is it offset based, or what sort of techniques do you use for that?
We use the signature-based.
Great. Thank you.